Hey everyone, welcome back. I'm Domingos. I'm also known as DMA and appreciate when I'm called DMA. So today we have this limit problem to find. We are given to find limit of a to the power x minus x to the power a over x minus a when x approach a. Oh, let's solve this limit considering that a is a positive number that belongs to the real numbers. Okay. Let's consider that a is a real positive number. Okay, to solve this problem, first of all, we know that when we're calculating limit, we have to substitute the value of x so that we see if the given expression obtained, if the obtained expression is undefined or defined. But if we substitute the value of x by a, on the numerator we'll have symmetric numbers, a to the power a minus a to the power a, and denominator the same. So we'll have 0 over 0, which is undefined. So we can solve this limit. Okay, since we are told not to apply L'Hospital rule, the first approach that we're going to use here will be letting the numerator, or the denominator, to be equal to a new variable. So for example, if we let x minus a to be, for example, equal to t. Now, let's consider this approach as like equal, for example, for instance. So we know that a is equal to x is equal to a. So for x go back to be equal to a, so that means t has to be 0, so that when I send a that side, it still becomes x equal to a. So that means for this case, t has to be equal to 0. In other words, t approaches 0 when x approaches a. So if we isolate here x, then that means x will be equal to a plus t, because it's negative goes that side positive. So substituting in our limits, then we're going to have limit. Now we're going to have t approaches 0, where there is a. We can now, since in the denominator we have x minus a, we can also factorize this order so that we have x first. So if we factorize, we're going to have negative, which will be x to the power a minus a to the power x over x minus a, if I factorize negative. So now, since let me just repeat first the expression here so that I substitute all at once. So since we are now substituting the new variable t, so we're going to have this will be equal to minus limit when t, in this case, when t approaches 0, and where there is x, we're going to replace by t plus a. So we're going to have t plus a to the power a minus a to the power t plus a over t, because we let x minus a to be t. So now, having this limit, we have plus on the exponent, so we have two expressions adding one another. Since it's a power, that means if they are adding before they were multiplying with the same base, so it's not wrong to say this is a to the power t times a to the power a, because they go back. So now, what happened? We know that t approaches 0. It's quite the same as saying t is equal to 0, just to minimize our expression. So if t approaches 0, that means if t is equal to 0, for instance, and if we replace here the value of t, we're gonna be having 0 plus a, which is only a. So if we do that, then we're going to have minus limit when t approaches 0. If we replace the value of t 0 here, then we're going to have a to the power a minus a to the power t times a to the power a over t. Now we can factorize a to the power a. So factorizing a to the power a, we're going to have minus limit when t approaches 0, a to the power a, 1 minus a to the power t over t. That's what we have. So a to the power a is a constant, can come outside. So we're going to have now, in this case, this is going to be equal a to the power a limit when t approaches 0. Now the question is, what about the negative here? If we check, this negative can enter multiplying here. 1 will become negative and a to the power t will become positive. So we're going to have now a to the power t minus 1 over t. This limit, it's easy to apply L'Hospital, but they say we are not required to apply L'Hospital, so we have to solve it narrowly. So what we can do now, so since we can't apply L'Hospital, we can let our numerator to be a function. So we can let our a to the power t minus 1 to be equal, let's say, to function y. So having that, what we can do, we can try to isolate what's the value of t. So a to the power t will be equal to y plus 1. So isolating t, then we can introduce logarithms both sides so that we can have the value of t. So what will happen in this case now, we're going to say that ln of a to the power t is equal to ln of y plus 1. So that t will be times ln of a equal to ln of y plus 1. Now this ln of a is multiplying, we can send that side dividing, so there is no need to be here. We can simply have t over ln a. So now, going back to our limit, we're going to have a to the power a times, now what happened if we check, we have t approximates 0. If we're introducing a new variable y, that means we have to now find out what's going to be the new value for y. Now, if t is equal to 0, for example, t is equal to 0, if t is equal to 0, we're going to have a to the power 0, which is 1, 1 minus 1, which is 0. So that means y is going to be 0. Or in other words, what has to be the value of y, so that this equation has t equal to 0. So if y is 0, this one can go that side, and 1 is a to the power 0, so t will be 0. So that means y is still 0. So that means here y still 0, y approximates 0. So we're going to have now a new limit with y approximates 0. Now a to the power t minus 1 in this case will be y over t. T is this expression, which is ln of y plus 1 over ln a. Okay, now this expression, it is y dividing this function. We know that dividing two fraction numbers is multiplying the first one by the inverse of the second one. So it's gonna be the same as if this ln 8 was on top. That's the same thing. But we have y here. Now, a question is it wrong if we say, instead of using the y on top, we use here, so that we can use it with ln? But the problem is, since y is on top, if we decide to put it here, it has to be inverted, like it has to be 1 over y. Why 1 over y? Because if there is 1 on top, so if we make 1 times the inverse of 1 over y, will still go to y. Now, this 1 over y, it is multiplying this ln, so that means can become the exponent of the argument of ln. So that means this 1 over y can come here, can come to the side as exponent. Now ln a is a constant, can come outside. So we're going to have a to the power a ln a limit. In other words, we can just do times 1 over, we know that when there is quotient, it's the same as limit of the numerator over limit of the denominator. So we can just find the limit of the denominator when y approximates 0, and we have ln of 1 plus y to the power 1 over y. That's what we have. Now if we check this limit here, we know that limit of log is the same as log of the limit. So we can alter that, we can change it. We can, instead of writing limit of log, we can write log of the limit. So doing that, we're going to have that this will be a to the power a ln a times, now this will be 1 over ln of the limit when y approximates 0 of 1 plus y to the power 1 over y. Okay. Now we can carry on. So now carrying on, we check that this expression, which I can write here, limit when y approximates 0 of 1 plus y to the power 1 over y. This is the identity for Euler, because this is equal to Euler. So if I substitute Euler here, I will be having now that our solution will be equal to a to the power a ln a 1 over ln Euler. And the ln Euler is 1 because it's the same as log of Euler to base Euler, which is 1. So this will be 1. then I will have a to the power a ln a. But this is a number multiplying ln, so it can become as an exponent of the argument of the ln. So this will be equal to ln of a to the power a to the power a. So therefore, the solution for this limit when a to the power x minus x to the power a over x minus a, when x approaches a, is the same as ln of a to the power a to the power a. So that is the solution. Okay, without applying L'Hospital. So if you enjoy, leave your like, your comment, subscribe, and most importantly, share with your friends.